Well, anyway now, because Manuel Perucho will talk about jet deceleration in radio galaxies and the FR dichotomy.
So thank you. Thank you very much to the organizers for inviting me to give in this talk. I will be talking, I will decelerate the story. So every information, all the information about the title was there. I will be talking about the process that makes some sources different, well, the process that we think that can make some sources different, some radio sources much different from others. And well, in this classical plot that in the end turns out to, distinct, in this map of luminosity and linear size, you can locate FR1 sources here and FR2 sources there. So what are the processes that are bringing the FR1s here, or even some of them down even at smaller linear sizes? So the first, let's see, it works. Okay. As an introductory note, Lang and Bridle last year published a paper in which they showed trends for FR1 jets that show continuous deceleration along the jet, and in some cases this deceleration occurs faster, but typically it's a continuous process. This is something to take into account. And then at the end of the deceleration process, you have very wide and slow down jets. This is the velocity, and this is like the jet radius. Right? It's like a parameter that gives us the position across the jet. So if you compare the maps of the radio maps and the X-ray maps, and via this modeling, they show that in all cases but one, the high emissivity region is correlated with the deceleration region. So there is a process of dissipation of kinetic energy that turns on the emission of the source and ends up with the deceleration of the jet. Also, Carve et al. Found X-ray jets in 15 out of 21 FR1s. And this again goes in the same direction. There is a process of dissipation of kinetic energy into internal energy and eventual emission. So the first simulation we tried to do to understand the deceleration processes in FR1s was inspired by a paper by Lang and Bridle in 2002, and we took the parameters of the modeling for the galactic medium by Hardcastle et al. In 3C31, and this is the density with distance, and this is the pressure with distance of this ambient. So, well, here you have the parameters, and what we got by the end of the simulation was this. This is like 15 kiloparsecs. We got initial expansion of the jet, possibly triggered by outflow conditions here, but in the end, the cocoon, well, this is the cocoon here, this is the jet, which becomes disrupted and turbulent downstream. And even if the recollimation shock is triggered by the outflow conditions here, eventually in real jets, the cocoon pressure drops as it expands. So you would have the jet, if conditions at the injection don't change, you would have the jet, you could find it overpressured with respect to the cocoon, and you could generate these kind of shocks. However, none of the models FR1 sources by Lang and Bridle in 2014 show features that tell us that there could be such a strong shock. As I said, things seem to happen in a more continuous way. So it could be like a series of small shocks or not such strong shocks. So in order to understand the influence of the ambient medium profiles in the evolution of jets, now I'm running a 3D simulation of a FR2-like jet, in which the density profile, this is the density profiles that we have been using in previous simulations. Now we are using this one, so the core, the galactic core is much larger, and the drop in density and pressure occurs at about 100 kiloparsecs. Sorry. We do this with our code, RADPenat, which is a 3D RHD code. So now, as we are working far away from the black hole, We assume that the magnetic field is not dynamically relevant. Of course, this is something that should be checked by further simulations. And we think, as Martin said before, that the magnetic field is not dominant at kiloparsec scales. This is something that observations tell you. However, we cannot strictly say that it's not dynamically relevant. It could have some importance. So this should be reviewed. So what we include also is a relativistic equation of state that allows us to deal with baryons and leptons separately. And this is a cut across the 3D grid. The box is like 256 kiloparsecs across. So this is what we are getting. This is I did this plot last week in a hurry, as you can realize. Here you have velocity. So there is a kind of oscillation, helical oscillation, and when you get to 100 kiloparsecs, a bit farther than 100 kiloparsecs, this oscillation becomes nonlinear, and you disrupt the jet. But still, you find it you have high velocity still there in the spine, so it's about 0.9 C. Here is density. You see the increases and decreases in density along the jet, which are due to these oscillations. So the oscillations are produced or generate changes in pressure, and of course in density too. And here you have the tracer or jet mass fraction, which tells you where the original jet particles are located. So this would be what you could see in radio if you would make a radio map, because these are all the hot particles, the ones that could trace the emitting particles. So Rossi et al. did simulations like this to study the evolution of instabilities in the long term, but in a homogeneous ambient medium. So basically, what we see here is that the most important result so far is that the instabilities which are induced at the jet basis, so we introduce small amplitude oscillations in the jet velocity injection, is able to disrupt the jet at a given distance, which coincides with the drop in density in the ambient medium. Another effect that the ambient medium may have is if it's inhomogeneous. These are simulations by Wagner and Bignell and Wagner et al. And you see that before the jet crosses this inhomogeneous region, this cloudy region, the morphology is very different from the one you expect from a homogeneous ambient medium. As soon as the jet has crossed this region, you expect this structure to develop when you get to the more homogeneous medium. By the way, in these simulations, we introduce inhomogeneities in the ambient medium too. You can see it's a bit slightly irregular. Only 10% inhomogeneities, 10% difference in density, I mean. So coming back to different processes of disrupting jets or decelerating jets, the FR1 paradigm tells us that jets are decelerated from entrainment, from the shear layer. They are entraining material from the ambient medium, and this shear layer can grow and get to the jet spine and decelerate the flow completely. And this idea is the one that is behind all these models that I cite here. So, how to produce such an entrainment, such a continuous entrainment from the shear layer to the inner spine? During my thesis, this is like 10 years ago, we did like lab studies of the growth of Kelvin-Helmholtz instabilities in relativistic jets. And what we did is, in order to understand all the process in detail, we did high-resolution simulations. This is 2D with periodical boundary conditions with a very small perturbation in pressure. So we let that grow. So we could follow the linear regime. As you can see here, this is the growth of the amplitude of the perturbations until the saturation and the eventual disruption of the jets. What's important about this is that we found like 3 regimes. One in which the jet was disrupted in a very sudden way, like in a flaring way, by long wavelengths compared to the jet radius. Another one in which the jet was pretty stable all the way through. This is, linear momentum in the jet as compared to the initial one with time of the simulation. And there's a third one, which is the continuous drop. Here you have the size of the mixing layer, of the shear layer, if you want to call it that way, with time, and you see that again, the flaring one, so for instance, that black solid line, it has a sudden increase. There are others that only grow very slowly, and others, they do it in a more continuous way. If you turn the time that a jet needs to be decelerated from its original axial momentum to, let's say, 10–20% of these original values, if you turn this time into distances, this gives you like from 300 to 3 kiloparsecs, which is basically the distances at which you expect FR1 jets to be decelerated. And it's a continuous process, right? Of course, as Sasha said before, magnetic fields can suppress the growth of Kelvin-Helmholtz instabilities, but still they grow. They grow slowly, but they grow, unless the magnetic field is really strong, and then you kill them. Okay, at the end of these simulations, if you take mean values of several parameters in a whole grid, in this box that we were simulating, what you find is that the jets that disrupt suddenly, this is the tracer, this solid line here, which is the jet mass fraction. 1 means pure jet original material and 0 ambient material. What you have here is like total mixing of the jet. And if you see the values for the velocities, which is the solid line here, you get at 0.4 at the end of the simulation. This is the jet radius, and you see that the jets are much wider than initially, right? So this is like 20 jet radii. Initially it was 2. Right? And then if you go to the continuous case, which is this one, or to those jets that keep stable all the way through, you see that the jets that slow down continuously, they show also a reasonable amount of mixing, and they keep still large velocities at the end of the simulations. So this process is very slow. It's being slow. So in order to decelerate these jets to subrelativistic velocities, you would need, as I said, up to several kiloparsecs. Not many, but several. And then, finally, the last group, which is the group of those jets that keep being stable, they develop very hot shear layers due to dissipation of kinetic energy into internal energy at the boundaries, and they keep basically the full speed. And they are a bit wider than initially. So we repeated this in 3D. In 2010, we got similar results. These are cuts across the grids, and these are mean values. And you see that, well, when you increase the Lorentz factor, I forgot to mention that the more stable ones are, of course, the ones which are faster. You see that the maximum in tracer in the model, in the Lorentz factor 5 model, you have like 0.2, which is 20% maximum jet mass fraction in a cell. So it's completely mixed. And as you go down, you see that in the faster jet, you still have a spine which has tracer 1. So it keeps a region of original jet material and mixed and fast. Whereas in the middle case, which was Lorentz factor 10, you have a transition from inside to outside, which is this one here, right? So, but all of them kind of have a continuous drop in this case in 3D. They don't develop strong shocks. I would like to finish this part on instabilities. I would like to mention that there is a possible case of a classified FR2 jet in terms of its luminosity that can be disrupted in kiloparsec scales. This is OA36 plus 710, which is a quasar jet. We are observing this with radioastron so space VLBI to get some information about what's going on close to the nucleus. But you see that the jet shows some oscillations, and that if you combine EVN with Merlin, you get this structure very far away from the VLBI jet, which is this region here. And this means that eventually these oscillations which grow with distance, by the way, can disrupt the jet. So still, instabilities can be able to disrupt powerful jets. And the last part of my talk will deal on mass load by stellar winds in jets, and there has been a number of papers on this, and the observational motivation comes mainly from CNA, which is a nearby jet, and you have all these spots there which have been interpreted by several authors as clouds or stars with let's say, powerful winds. And Sarkowicz will be talking about this later. This scenario has been claimed to be a possible way to mass load jets because the stellar wind is able to stop the jet at a given distance to the star, and then you form this bow shock and a cometary tail, and when this cometary tail becomes unstable, you can mass load the jet with this baryonic gas. So in addition, this has been claimed to be a possible source of high energy radiation. Yesterday I mentioned the work by Barkov et al., but the original paper was by Bednarek and Prothero. They claimed that you could produce gamma rays from star-jet interactions, and there has been a number of papers ending in those that Sarka will present later. So here, what you take into account is that there are stars, there are clouds that are just orbiting the black hole, and some of them might get into the jet. And then, of course, once you are in, then you have the shock, you have the tails, you have the mass load. So what we did was to catch on Komisarov's idea and some numerical calculations. They were not simulations because they were steady state, so they just integrated the equations a long distance by Bowman et al. And we performed simulations of leptonic jets starting at like 80 parsecs from the black hole with an initial radius of 10 parsecs. And we added source terms in the equations of relativistic hydrodynamics, source terms that took into account, or to take into account, the possible mass load by a single population of stars in these simulations. So with winds that are not really powerful, at the 10 to minus 11, 10 to minus 12 solar masses per year, as suggested by different papers that Bowman et al. Referred to. I don't recall the authors now. Sorry about that. So this scenario that had been studied in the case of 3C31, is this number, I will recall it later, about a factor of 10 to 44 ergs per second, could be is not enough to decelerate this jet in particular. So in 3C31 you need something else, like entrainment from outside. But so we thought let's take into account less powerful jets. So here you have the set of parameters that we were using. Here we have, let's say, the most powerful jets in the sample, and then we have jets that are like 5 times 10 to 41 ergs per second. So they would correspond to low luminosity radio galaxies or to safer galaxies. So very weak jets. And then, well, the jets are very dilute. In this case, we have like 10 to the minus 10 times the density in the jet as outside, and different values for the mass load. This is the value that normalizes the mass load. Here you have the equation. This is the projected. We had to deproject this nuclear profile. It's Lauer et al. Sorry, this was the reference. It was here, and then we introduced again this decrease in density, and with this galactic atmosphere coming again with the parameters that we had used in the simulation for 3C31, so Hardcastle et al. 2002, and introducing this mass load by stellar winds with these mass losses, as I said before, we got these results. Here you have the leptonic mass fraction, so the amount of leptons that you have in the jet with respect to the total mass in each cell. And you see that already at the first cell, it's less than 1. So you are mass loading the jet from the injection at this distance. And assuming that you could have more stars even closer to the black hole, the jet might be mass loaded really close to the inner region. And then you get down to, like, this is 0.01 at less than 1 kiloparsec. This is the axial velocity. You see that the jet expands and the velocity drops with distance until a flaring point. And here you have the density map, which you see again the spine is expanding and then mass loading and becoming flaring and turbulent. These are the cuts for the jet velocity along the jet, for the cases in which the jet was slightly more powerful or had less, it had less mass load, like in this case it's 1 order of magnitude less than in the other cases, or no mass load. So what you have there is is pinching, some oscillations, and because these are axisymmetric to these simulations, and then eventual disruption by the growth of this pinching. This happens at about 1 kiloparsec too, but these are very weak jets, so they are more prone to develop instabilities. But if you include the mass load, this is what happens with the axial velocity. It drops continuously until, they also flare, but they flare in a more violent way because of the growth of instabilities is becoming faster as the jet becomes decelerated. So the distances at which we found this flaring coincide basically with the expression that was given by Hobart and Blackman, in which you just estimate the distance at which the jet cannot handle with all this mass load anymore. I mean, cannot propagate further with this mass load. And still, by the end of or after the flaring, you still have velocities of the order of 0.3, 0.2 c in these ones, and this is like 0.1 c here. So if we pay attention to the expansion of the head of the jet, see that 10 to 44, 3C31, and the two powerful models in this set of simulations, they just grow with distance and they don't care about the mass load, right? So in this case, with this atmosphere and with these mass load rates, maybe a different stellar population would make a difference, but with this one, they just don't pay attention to that. Then, if you have a less powerful jet with a factor 10 less mass load than the fiducial one that we have used, or no mass load, you have slower expansion, but expansion. However, in the case of the simulations with the maximum value of mass load, you have eventual deceleration of the head, and well, this would be eventually compatible with zero velocity. So the head would be stuck there, right, in these jets. And I come to my conclusions. The jet power and the environmental properties, including stellar population, seem to determine the evolution of radio sources. The jet deceleration can be produced in relativistic hydrojets by strong recollimation shocks in steep density gradients. However, this is not tremendously supported by observations. So as I said, you expect more continuous processes of deceleration as the modeling of FR1 jets shows. You have small scale instabilities in less powerful jets that can cause mixing, dissipation, increase of internal energy, expansion of the shear layer, because when you increase the internal energy, you increase the pressure, you expand your shear layer, you mix more gas, and then you continuously expand and decelerate your jet. This mixing layer grows outwards and may grow inwards too. And then you may have long wavelength instabilities, that can cause disruption of even powerful jets, as I show you for your case of the quasar 036 plus 710. And just to finish a small comment, this is a question more than a comment. In the FR1 images that I showed in the beginning by Lang and Brie that you see, and many authors also, there's a very nice picture of NGC 315 by Worrell et al. You have an oscillation of the jet before it finally disappears, the spine finally disappears. And this oscillation, could it be also the development of an long wavelength instability in the shear layer between the spine and the shear layer itself and the mixing layer, And finally, remarking that mass load by stellar winds and clouds can efficiently decelerate jets depending on the jet power and the stellar population. I think Sarka will talk more about that. Thank you very much.
Denise, yeah. Ladies first.
Thank you. Okay, you showed I don't remember what source it was, but it was a VLBI jet. It might be 08 something.
036,
that you fitted, forward, that one. Yeah, that you fitted with Kelvin Helmholtz instabilities.
Not really. What we said is that there are instabilities.
My question is, would it be worth trying to model something like that with a magnetic instability, like a kink instability?
Sure.
Because these are still small scales.
The point is that the distances here are this. I mean, if you project this jet, is like 10 kiloparsecs. So at 10 kiloparsecs, I don't think that current-driven instabilities or kink instability in this case would dominate the growth. That's why we think it could be Kelvin Helmholtz, unless this jet is magnetically dominated up to the end.
It might still be worth giving it a try and seeing what kind of
sure. The problem is that current-driven instabilities in relativistic jets, I mean, the theory is not very well developed so far. Yeah. But sure.
I have two questions on two of your conclusions. Firstly, on the small scale instabilities on the Kelvin-Helmholtz, I guess this and the final result will be a bit of a resolution dependent because you'll not be converging. But can you isolate how much of energy you are dumping in the sheath of the jet, and then convert, because this will be radiated in some way, and then compare with observations and then try to constrain?
Well, that depends.
How efficient is it?
Yes, that can be done. It depends on the wavelength, because if you have very short wavelengths, like less than 1 jet radius, you can develop these instabilities in very small scales there. You dissipate lots of energy and you create this very hot surrounding, very hot layer surrounding the core. And then I would expect some limb brightening of these jets too. However, we have seen other mechanisms to limb brighten jets, so I don't know which one is the.
And have you done a convergence study to see the effect of resolution on this, on the Kelvin-Helmholtz?
Yeah, well, in the Kelvin-Helmholtz instability case, yes, I did. Actually, these 2D simulations were 2D because the resolution had to be really high to follow the linear regime. Yeah.
And the last question on the last point on the mass loading of the jet.
Yep.
So, people were talking the relativistic jets have this singe gas equation of state for this jet chi parameter, rho c square by enthalpy. So I was very interested to see that the leptonic power drops off and the jet becomes mass loaded. So can you give us an estimate of what is the chi parameter variation from like up in the head of the jet? Does it become heavily mass loaded as you go up?
At the head of the mass loaded jets, I mean the leptonic mass fraction is ridiculous. So I would say it's like proton electron flow at that point. Right?
Okay, thanks. Gopal, next.
Comment that there is a sizable population of high redshift quasars, Z greater than 2, which must be having very powerful jets because you see them, they are extended structures. However, which do not produce hotspots or very little of hotspots. So they are all getting disrupted. But my question was, based on your simulations that you presented in the earlier part of your talk, can you say something about the evolution of the cocoon that was formed in the earlier stage before the deceleration took place?
And these ones? This one?
Yes.
Okay, here this jet is very slow. So here we have the ambient medium is in hydrostatic equilibrium, so you have some pseudo gravitational field there, and in order to stop it from moving, because you have a decreasing pressure, so you end up forming this kind of spherical, not cocoon but mixed region that you wouldn't see, because you see what you would see in radio images would be the spine and maybe something here where you still have hot material. And then when you get to the drop in density in the ambient medium, the jet head accelerates a bit, and then you detach from that. But in the long term, what you would see would be this head, and this would be mixed up with the shocked ambient medium.
Thank you. Two more questions. Often Robert, the last one.
So you have this spine, and then you have shear layer. So do you expect the photons from the shear layers get inverse Compton scattered from the spine at the layer, separating them, and then you should have a component in the flux? So
well, it may happen. I mean, this is all thermal gas, right? So we didn't run so far emission simulations from this. So it is possible, yes.
I'll just comment on the last question, if I may, quickly. I think in these deceleration regions, the relative velocities of the spine and the shear layer are actually too low to produce this, but further in,
that's true.
For example, the Ghisolini et al. Model is appropriate indeed. The comment I was going to make was about dissipation in the deceleration region, which is there are a number of reasons to believe this is happening, a number of clues to the way it's happening. One of which is, of course, X-ray emission, as you mentioned. The second is that if you try and model this, model the radio emission with an adiabatic, just with adiabatic losses, you fail completely. You need an additional particle injection mechanism to do that. And the third point is that we think there is a dependence of the new electron injection on velocity, because if we look at the spectral index very carefully in these regions, we find that the spectral index is slightly steeper, counterintuitively, where the jet is going faster. And that's actually quite a clean result for the 10 or so objects we've looked at. We published that in 2013. So there's quite a lot of evidence that there are rather complex deceleration and injection mechanisms going on there.
Okay, thanks a lot for the discussion and for the